I would like to first thank the organizer for giving me this opportunity to share our works in this wonderful workshop. Today, I'd like to share possible bias in the weak lensing mass estimate in emerging galaxy clusters. So, according to our cosmology, understanding of the cosmology, galaxy clusters are formed under this large-scale structure, as you can see from the dark matter distribution of millennium simulations. At this node of intersect of multiple filaments, you can see there is an overdensity form, and at the very center, you can find your very favorite cluster, like Abel S1063. You can see a lot of galaxies floating in a very compact space of the universe. I think we discussed multiple times throughout this conference, but one of the most important aspects of the galaxy is, of course, the mass of the galaxy clusters. Clusters of galaxies are the end product of this hierarchical mass assembly. So their cluster mass basically proves this underlying cosmology. As you can see on the halo mass function, cluster mass function on the x and the number density, you can see the numbers of the clusters varies with the different cosmological model where we can test this cosmology. Throughout the conference, we have talked about different methods of measuring the mass of the cluster, and today I'd like to specifically focus on the weak gravitational lensing using the example figure shown in An et al. 2025, which you've heard in the wonderful talk yesterday. The basic concept of weak gravitational lensing starts with the background selections. So we have this galaxy selected from the images. We identify the red sequence of the cluster member galaxies, and then select the background galaxies, for instance, by selecting those are fainter and bluer. With a complex modeling of the point spread function modeling and all these details, we get this weak lensing mass contours by averaging the shape of the background galaxies, as you can see in the contour, which basically agrees with the galaxy distribution as we can predict. Here we can see a two mass state, one in the north and one in the south. And what we can do is we can measure the mass of the individual system by fitting a models. So for instance, here we fit in W profiles with assuming mass concentration relations, which gives a mass of uncertainty of 30 to 10% depending on your source density and your telescopes. But since, as you can see, weak gravitational lensing deals with the weak signals of the few percent of the shape distortions. So it requires a model assumption at multiple steps. And the question goes to, does this assumption create a bias or scatter, as we learned on the statistics course with a high accuracy with low precision, and vice versa. And as my talk title was showed, I would like to focus slightly more on the specific target emerging galaxy cluster. Like you see in the Boulder cluster, as Sungjun showed earlier, you can see this beautiful X-ray dissociated completely from this dark matter halo because of the recent merger activity, direct force exerted on the intracrust medium. In this system, of course, the X-ray related properties or SE pressure maps would be affected by this ongoing merger activity, by the compression and the heatings. And so the weak lensing actually is one of the only reliable mass estimates to get the total mass of the system and the individual mass of these colliding clusters. So the question we had was, can weak lensing provide an accurate mass estimate in this complicated, this very energetic event in this universe? To test this idea, we have started an idealized cluster merger simulation. We run a Gamer 2 simulation, which is adaptive match refinement code. We start with the two clusters placed in a closed box and separated by 3 nanoparsec. We vary different cluster properties, including the mass, initial velocity, and impact parameters, that design this cluster to be stable at their initial condition following a W profile and ICM having the modified beta profiles. And then on the simulated set, we have cropped the mass distribution on 5 nanoparsec by 5 nanoparsec regions and performed a mock weak lensing analysis, assuming a realistic shape and background galaxies. For this, we have assumed an intrinsic shape errors of 0.25, and for the measurement errors and the source density, we use the values that we had from the previous observation of coma for hyperspace prime beta and El Gordo for the HSC observation, which gives about 25 to 100 galaxy per arc minute square. And the right figure shows the histogram of the measurement error from the observations of each telescope and the mock catalog that we created, so you can see how we try to mimic the observation as best as we can. So we located this cluster mass distribution at redshift 0.2 and this background galaxy at redshift 1.0 to perform the mock reclassing analysis. So in a nutshell, we have this idealized cluster merger simulation, which basically gives the true N200 directly from the simulations. And then we can perform a mock reclassing analysis, which gives a reclassing mass estimate, as we can do from the observations by an anecdotal profile, and in this case, assuming MC relation from Daniel 2008. And this shows our results. So here, what we compare is on the x-axis is the time since the first parasitic passage, and the y-axis shows the reclassing mass estimate at each time step compared to the N200. At the parasitic passage, of course, the two halo overlap, so we cannot distinguish two of them, so we skip this epoch. And after those, you can see there is a trend for both subcluster and the main cluster. In short, we can see the mass are both overestimated at the early merger phase, and then it goes to an underestimation of the mass on the late merger phase. We check different merger parameters, and for this case, where the main cluster is 10 to 15 solar mass and the subcluster mass is 10 to 14 solar mass, you can see this impact on the main cluster is small, but as we increase the mass of the subcluster up to 10 to 15 solar mass, you can see that first of all, in all merging clusters, we see a common trend of overestimation of the mass at the early phase and vice versa for the late phase. And secondly, you can also see the amplitude of the reclassing mass bias shows a clear dependence with the increasing mass of the subclusters. And if we summarize this maximum bias of reclassing mass estimate in the given combination of the initial condition mass of subclusters and the initial mass of the main cluster, you can see that both mass of the main cluster and the subcluster present a clear increasing trend of mass estimate up to 50% in the most massive merging clusters. And I want to note that this 50% is obviously larger than the reclassing mass uncertainty, which could be a problem in some cases. Since it's a simulation, we can play with the particles, so we try to tackle what caused this reclassing mass bias. So we select this epoch of the maximum mass estimate of the main cluster and check the concentration of the cluster, both cluster, the sub in the blue, subcluster in the blue, and the main cluster in the red. First of all, you can see that halo concentration is definitely larger than the initial concentration, which is assumed from the mass concentration relations. And this is actually not surprising because we can expect that the cluster started from the stable stage. And when the cluster pass each other at the parasitic passage, the gravitational potential overlaps and increase the potential. So it starts to contract and increase the concentration. And of course, at the late phase, they are now apart from each other at the epicenter, and they will expand due to the end of these contractions. So basically, we are seeing the halo profile is changing from the initial NFW profile, as we actually discussed yesterday. Are we happy with NFW? So if we fit a model here, we can imagine that halo is having a higher concentration than the initial stage, but we are still assuming a diffuse model over these halos. And if we actually divide this to halo over models on the simulated data, you can see that the central regions are mostly underestimated because reclassing tries to mimic the central regions, and you can see this white region here, but overall the outskirts are definitely overestimated, which gives the total mass estimate of the reclassing to be larger than the true N200. So you can consider this overestimation as a part of a model bias. So we try to answer, is this a bias or scatter? Short answer, we track this single halo fitting over the longer time scale, and you can see there is a fluctuation, but there is also a dependence on line of sight merger or Planck sky mergers. So if we can randomly select the cluster at different time and different viewing angles, it will give us around 10% of scatter, which actually agrees with our understanding of fitting a NFW profile on a triaxial payload on random directions. But if, as we've seen with this figure, if we select a merging cluster at a specific time step, like early or late phase, your mass estimate could be biased, which means we need a solution to resolve this bias. In the remaining time, I would like to show the two methods that we found in correcting the frequency mass bias. We test different ideas, but we got this result of reproducing the frequency mass estimate, reproducing the N200 when we give the frequency mass fitting the true concentration that we derive from this halo fittings. This means that the frequency mass estimate could reproduce the actual mass of the cluster if we can understand the modified halo profile of these merging galaxy clusters. And the way to do that, of course, is, I think, recleansing combining with the strong lensing analysis. As you've heard from Sang-Jun's talk earlier, strong lensing can constrain the mass distribution of the very central regions of the galaxy cluster, while recleansing probes the mass distribution on the outskirts of the clusters. And using this combined analysis, Boson made a nice estimate of the mass of these merging galaxy clusters, and of course you can check the result and the detail on Boson's cluster number 2. And the second method would be, like any other astrophysical problem, machine learning. For this, it's a very preliminary stage, so I'll just go brief. We created a mass map of a TNG cluster, thousands of clusters projected in random directions, and then train this convolution neural network, modeling both mergers and non-merger systems. Sang-Jun Cha is leading this machine learning project, and the result is quite promising, having this true mass map on the x-axis and reconstructed mass M200 from the CNN is nicely following the M200. So we are working on this, testing different ideas, but CNN models could be an effective way to reproducing M200. So here's a summary. I think frequency analysis is effective still, because we are only seeing a scatter in the random samples. But if you're working on a cluster at a specific merger phase, there could be a bias in the frequency mass estimate up to 50%. I'll link this summary slide, and thank you for your attention.
Any questions for Wangi?
Hi, thanks for the talk. I was just wondering about the concentrations, because how do you even measure concentration of two merging objects? I just know that even if you measure concentration in R500, R200, those can be different values already. Like if they're merging, you cannot go to such large radii. So.
Yes, that's one of the points. So for this analysis, what we did is since it was idealized simulation, we know the particle IDs from the starting points. So even in the post-mergers, we have plotted this, each individual halos only using their original IDs that measure the concentration over there. So it won't be applicable, of course, for the observation setups, but since strong lensing could constrain the mass within a specific radius, it will give a similar constraint on the final mass estimation.
Any other questions? Yanti?
So I'm not sure how to take from your talk. So there is this bias, which you said averaging over different parameters or over time, it will bias the mass estimates up to 50% or on average 10%.
Okay. Yes.
And then, so your colleagues have made measurements of various merging clusters. So how robust are those mass estimates?
Yes. So I think the main point is that first of all, specifically on merging cluster, like I'm working on radio-well cluster mergers, which is the recent colliders. So that's why we started the project of whether we can weak cleansing mass estimate would be precise in those specific sample of merging clusters. Of course, there is a mass bias predicted from the numerical simulations, but obviously we have started with assumption from the simulation as well. For instance, we are starting with these pre-mergers are starting with a stable NFW profiles, and we are assuming that they were following the mass concentration relations. So there were some open questions for those, as we are also using different mass concentration relations in observations. But I think we should say that we should take caution in averaging multiple merging systems with the frequency assessment.
Okay, time's up. Let's thank Won-gi one more time.